Tonight, we're going to explore something hiding inside every atom in your body. Something so small, it has never been seen directly, yet so powerful, it defines what matter actually is. The proton. You were probably taught that protons are tiny solid particles sitting in the nucleus of an atom. Simple little building blocks of matter. But that picture is completely wrong. A proton is not a thing. It's a storm. A violent, seething hurricane of energy and force that never stops raging. And here's the part that will change how you see everything. Almost none of the proton's mass comes from the particles inside it. Almost all of it comes from pure energy. The stuff you're made of, the mass you feel when you step on a scale, is almost entirely energy pretending to be matter. Before we go any further, if this kind of deep exploration resonates with you, a quick like or subscribe would mean a lot. Your support genuinely helps more than you know. Now, let's begin. Let's start with something you know. Something you've experienced every single day of your life, without giving it a second thought. Touch the surface in front of you right now. A table, a desk, the arm of a chair, your own hand resting against your leg. Whatever it is, it feels solid. It feels like something is there. Something real, something substantial, something you could push against and it would push back. Your entire experience of the physical world is built on this sensation. Solidity. Resistance. The feeling that matter is stuff, that it has substance, that it takes up space and has weight, and exists in a way that's tangible and undeniable. You've relied on this feeling since you were an infant, reaching out to grab the bars of your crib. Solid things are solid. It's probably the first fact you ever learned about the universe, long before you had words for it. Pick up a rock sometime. Feel its weight in your hand. It's heavy. It resists your grip. Squeeze it and it doesn't give. Drop it and it falls because gravity pulls on its mass. Kick it and your toe hurts because the rock pushes back against your foot. The rock feels like it's made of something. Dense, compact, real. Something is in there. And if someone asked you what gives the rock its weight, what makes it heavy, you'd probably say something like the atoms inside it, the stuff it's made of, the material. That seems obvious, doesn't it? The mass of a rock comes from the mass of the atoms that make it up, and the mass of those atoms comes from the particles inside them. Smaller things make up bigger things, and the mass just adds up. It's simple, it's intuitive, it's what you'd learn in any basic science class, and it's almost entirely wrong. But we'll get to that. First, let's talk about what we think matter is, because humans have been asking this question for a very long time. Thousands and thousands of years. Probably as long as we've been capable of abstract thought. We've been looking at the world around us and wondering what it's made of. What is this stuff? Why is rock different from water? Why is wood different from metal? What is the fundamental essence of things? And the answers we've come up with have changed dramatically over time. Each new answer has been stranger than the last. And the current answer, the one modern physics gives us, is the strangest of all. The ancient Greeks were the first people we know of who seriously tried to figure out what matter is made of. Different philosophers had different ideas. Thales thought everything was made of water. Anaximenes thought it was air. Heraclitus favoured fire. Empedocles proposed that everything was a mixture of 4 elements: earth, water, air, and fire. These ideas seem primitive now, but they represented a genuine attempt to understand the fundamental nature of stuff. Around 450 years before the Common Era, two Greek thinkers, Leucippus and his student Democritus, proposed something radical. They suggested that if you kept cutting matter into smaller and smaller pieces, you'd eventually reach a point where you couldn't cut anymore. You'd arrive at the smallest possible piece of matter. They called these pieces atomos, which means uncuttable or indivisible. In their view, everything in the universe was made of these tiny, indestructible particles moving through empty space. Different types of matter were simply different arrangements of atoms. Change the arrangement and you change the substance. It was a brilliant idea. It was also almost completely ignored for over 2,000 years. Most Greek philosophers preferred Aristotle's view that matter was continuous and infinitely divisible. The atomic idea gathered dust, while other theories dominated Western thought. But the atomists were right. They were right about nearly everything. Matter really is made of tiny, discrete particles. The universe really is mostly empty space, and different arrangements of particles really do produce different types of matter. They guessed all of this from pure reasoning, without microscopes, without laboratories, without any of the tools we now take for granted. The modern atomic theory didn't emerge until the early 1800s, when an English school teacher named John Dalton revived the idea. Dalton was studying how chemicals combine with each other, and he noticed patterns that couldn't be explained by the prevailing theories. He found that elements always combined in fixed ratios. Water always contained hydrogen and oxygen in the same proportions. Carbon dioxide always had the same ratio of carbon to oxygen. No matter where you got the water, no matter who made the carbon dioxide, the ratios were always the same. This made perfect sense if matter was made of atoms. Each type of element consisted of identical atoms with specific weights. Chemical reactions were just rearrangements of these atoms. You weren't creating or destroying matter. You were shuffling particles around, snapping them apart and reconnecting them in new combinations. Dalton published his atomic theory in 1808. He proposed that atoms were tiny, solid, indestructible spheres. Different elements had different types of atoms with different masses. Compounds were formed when atoms of different elements combined in simple whole number ratios. This was a powerful theory. It explained chemical reactions beautifully. It predicted how elements would combine. It gave chemistry a solid mathematical foundation that it had never had before. For the first time, chemistry became a precise, quantitative science, rather than a collection of recipes and observations. But Dalton was wrong about one crucial thing. He thought atoms were indivisible. He thought they were the smallest possible things, fundamental particles with no internal structure. Solid little billiard balls that could be rearranged but never broken. This turned out to be spectacularly incorrect, and the person who proved it changed everything. In 1897, a British physicist named Joseph John Thomson made a discovery that shattered the idea of the indivisible atom forever. Thomson was experimenting with cathode rays, streams of mysterious glowing material that appeared when you ran electricity through a glass vacuum tube. Scientists have been arguing about cathode rays for years. Some thought they were waves, others thought they were streams of particles. Nobody knew for certain what they were made of. Thomson carefully measured how these rays responded to electric and magnetic fields. By applying both and seeing how the rays bent, he could calculate the ratio of the particles' charge to their mass. What he found shocked the scientific community. The rays consisted of tiny particles much smaller than any atom, far smaller. These particles carried a negative electric charge, and they were identical regardless of what material the cathode was made from. It didn't matter if the tube used an aluminum cathode or a copper cathode or a platinum cathode. The same tiny particles came out. Thomson had discovered something that existed inside atoms, a subatomic particle, a piece of the supposedly unbreakable atom. He called them corpuscles. We now call them electrons. This was revolutionary. If atoms contained smaller particles, then atoms weren't indivisible. They had internal structure. They were made of something even more fundamental. Thomson proposed what became known as the plum pudding model. He imagined the atom as a sphere of positive charge with electrons embedded in it, like raisins in a pudding. The positive charge was spread uniformly throughout the atom, and the negative electrons sat inside it, balancing the overall charge to make the atom electrically neutral. It was a reasonable guess. It was also completely wrong. In 1911, a New Zealand physicist named Ernest Rutherford performed one of the most important experiments in the history of science. Working at the University of Manchester with his colleagues Hans Geiger and Ernest Marsden, Rutherford directed a beam of alpha particles, which are tiny positively charged particles emitted by radioactive materials, at a thin sheet of gold foil. If Thomson's plum pudding model was correct, the alpha particles should have passed through the gold foil with only slight deflections. The positive charge in the atom was supposed to be spread out evenly, so there would be nothing dense enough to significantly deflect the fast-moving alpha particles. Most of the alpha particles did exactly what was expected. They passed straight through the foil as if it wasn't there. But some of them deflected at large angles, and a few of them bounced almost straight back toward the source. This was shocking. Rutherford later described his astonishment by saying it was as if you fired a 15-inch artillery shell at a piece of tissue paper and the shell came back and hit you. Something inside the gold atoms was dense enough and concentrated enough to bounce alpha particles backward. The positive charge wasn't spread evenly through the atom. It was concentrated in a tiny, incredibly dense point at the center. Rutherford had discovered the atomic nucleus. The implications were profound and deeply unsettling. The nucleus contained nearly all of the atom's mass but occupied only a tiny fraction of its volume. The rest of the atom was empty space with electrons orbiting far from the center. How empty? Let's put this in perspective because it's genuinely one of the most difficult things about atoms to wrap your mind around. If you scaled up an atom so that the nucleus was the size of a marble, about 1 centimeter across, sitting at the center of a football field, the electrons will be orbiting at the edges of the stadium's upper seats. Everything in between, the entire playing field, all the stands, all the concession areas, everything would be empty. Nothing there, just space, vacuum, void. The atom, the thing that makes up all matter, the thing that makes up your bones and your blood, and the chair you're sitting on, is overwhelmingly empty. More than 99.9999999999% empty. That's not an exaggeration, it's a measured fact. If you removed all the empty space from all the atoms in every human being on Earth, the remaining matter would fit comfortably inside a sugar cube. All 8 billion people, compressed into a cube you could hold between your thumb and forefinger. That's how empty atoms are. That table you touched a few minutes ago, the one that felt so solid, it's almost entirely nothing. The reason it feels solid has nothing to do with the material actually being there in the way you think. It's because the electromagnetic forces between the electrons in your hand and the electrons in the table repel each other. The electron clouds push against each other, and your brain interprets that electromagnetic repulsion as the sensation of touching a solid surface. You're not touching matter, you're feeling force. You've never actually touched anything in your entire life. Not really. Not in the way you think. Every contact you've ever made with another object was electromagnetic force fields pushing against each other across mostly empty space. But let's keep going, because the story only gets stranger from here. Rutherford had found the nucleus, and he knew it was positively charged. In 1919, he performed another experiment that identified the source of that positive charge. By bombarding nitrogen gas with alpha particles, Rutherford knocked out particles from the nitrogen nuclei. These ejected particles had a positive charge exactly equal in magnitude to the electron's negative charge, and they had a mass roughly 1,836 times greater than an electron. These were protons, hydrogen nuclei, the simplest possible atomic nucleus consisting of just one of these positively charged particles. The proton became recognized as a fundamental component of the atomic nucleus. Its positive charge balanced the negative charge of the electrons, making atoms electrically neutral overall. And here's what made the proton especially important. The number of protons in the nucleus determined what element an atom was. This was a profound realization. One proton and you have hydrogen, the lightest and simplest element. 2 protons and you have helium, the gas that makes balloons float. 6 protons and you have carbon, the backbone of every living molecule. 7 protons give you nitrogen, the gas that makes up most of our atmosphere. 8 and you have oxygen, the element we breathe to stay alive. 26 and you have iron, the metal at Earth's core. 79 and you have gold. 92 and you have uranium. The proton is what gives each element its identity. Change the number of protons and you change the element entirely. Turn Lead into gold? That means changing the number of protons from 82 to 79. The alchemists were trying to do nuclear physics without knowing it. The proton was clearly important. It was the particle that defined the very identity of every element in the periodic table. But there was a problem with the nucleus that protons alone couldn't explain. The masses of atoms didn't match what you'd expect from protons alone. Helium, for example, has 2 protons, but its mass is roughly 4 times the mass of a single proton, not 2 times. Something else was inside the nucleus alongside the protons. Something with mass but no electric charge. Something invisible to the electromagnetic experiments that had found the proton. In 1932, James Chadwick, working in Rutherford's laboratory at the Cavendish Laboratory in Cambridge, solved this puzzle. By bombarding beryllium with alpha particles, Chadwick detected a new type of radiation being ejected. This radiation could knock protons out of paraffin wax, which meant it had to consist of particles with substantial mass. But these particles carried no electric charge, which is why they have been so difficult to detect. Electric charge is how we see most particles, We detect them through their electromagnetic interactions. A particle with no charge is essentially invisible to most detectors. Chadwick managed to measure the new particle's mass by studying the way it collided with other particles. It had almost exactly the same mass as the proton, but carried no electric charge. He had discovered the neutron. Now the picture seemed complete. The atom consisted of a nucleus made of protons and neutrons, tightly packed together at the center, surrounded by a cloud of electrons at much greater distances. Protons carried positive charge. Neutrons were electrically neutral. Electrons carried negative charge. The number of protons defined the element. The number of neutrons could vary, creating different isotopes of the same element. Hydrogen usually has one proton and no neutrons. But deuterium, also called heavy hydrogen, has one proton and one neutron. Tritium has one proton and two neutrons. All three are hydrogen because they all have one proton, but they have different masses because of the different neutron counts. The electrons, meanwhile, determined chemical behavior, how atoms bonded with each other to form molecules and materials. It was a clean, elegant picture. Protons and neutrons were the building blocks of the nucleus. Electrons orbited around them. Together they made atoms. Atoms made molecules. Molecules made matter. Matter made rocks and water and stars and people and everything else in the universe. Physics had reached the foundation, or so it seemed. For about 30 years, this model held. Protons and neutrons were considered fundamental particles, meaning they had no internal structure. They were just tiny, solid objects with specific masses and charges. The proton had a mass of about 1.67 times 10 to the negative 27 kilograms. A truly minuscule number. If you wrote it out, that's 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 measurable quantity. The proton had mass, and that mass was assumed to be an intrinsic property of the proton itself. Whatever the proton was made of, that's where the mass came from. Simple. But there was always something slightly unsettling about treating protons and neutrons as fundamental. For one thing, there were too many supposedly fundamental particles. By the 1950s and 60s, particle accelerators were smashing atoms together at higher and higher energies, and they kept discovering new particles at an alarming rate. Pions, kaons, sigma particles, Xi particles, lambda particles, eta particles, rho mesons, dozens upon dozens of particles that seemed to behave like cousins of the proton and neutron. They appeared in high-energy collisions, lived for extremely brief moments, sometimes just trillionths of a second, then decayed into other particles. Physicists called this bewildering proliferation the particle zoo. And just like a zoo, it needed organizing. It needed someone to figure out which animals were related to which ones belonged in the same family, and what underlying principle could explain why there were so many of them. If there were this many particles, maybe they weren't all fundamental. Maybe some of them, or all of them, were made of something even smaller. Maybe protons and neutrons were not the bottom of the ladder after all. Maybe there was another layer beneath, another level of structure waiting to be discovered, just as Rutherford had discovered structure inside the atom, and Thomson had discovered electrons inside what was supposed to be indivisible, The first serious hint came from experiments measuring the proton's properties more carefully. The proton has what's called a magnetic moment, a measure of how it behaves in a magnetic field. If the proton were truly a point-like fundamental particle, its magnetic moment could be calculated precisely using quantum mechanics. But when physicists measured the proton's actual magnetic moment, it didn't match the prediction. It was about 2.8 times larger than what a simple, structureless particle should have. This was a clue. A structureless particle wouldn't have an anomalous magnetic moment like this, but a composite particle, something made of smaller charged components moving around inside it, would. The proton was hinting that it had internal structure. Something was moving inside it. In 1956, Robert Hofstadter at Stanford University performed experiments that strengthened this suspicion enormously. Hofstadter fired high-energy electrons at protons and carefully measured how the electrons scattered. If the proton were a simple point with no size, the scattering pattern would follow a specific mathematical prediction called the Mott scattering formula. But Hofstadter found that the pattern deviated from this prediction in a very telling way. The proton wasn't scattering electrons like a point. It was scattering them like an object with a physical size and an internal distribution of charge. The charge wasn't concentrated at a single point. It was spread out over a tiny but measurable volume. The proton had spatial extent. It wasn't a point. It was an object roughly 0.87 femtometers across. A femtometer is 1 quadrillionth of a meter. That's 1 millionth of 1 billionth of a millimeter. To put that in perspective, a femtometer is to a millimeter what a millimeter is to the distance from Earth to a point well beyond the orbit of Jupiter. Unimaginably small, but it was a real, measurable size. And that size meant something profound. Hofstadter won the Nobel Prize in Physics in 1961 for this work. His experiments proved the proton was not elementary. It had structure. It had a shape, a charge distribution, and inside, something was in there. But what? What could possibly be inside something that small? By the early 1960s, the situation in particle physics was chaotic. The particle zoo kept growing, new particles kept appearing, and no one had a convincing theory to explain why there were so many of them or what they were made of. Two theoretical physicists, working independently, proposed the answer almost simultaneously. In 1964, Murray Gell-Mann at the California Institute of Technology and George Zweig at CERN both proposed that protons, neutrons, and all the other particles in the zoo were not fundamental. They were made of even smaller particles. Gell-Mann called them quarks, a name he borrowed from a line in James Joyce's novel, Finnegan's Wake. The line reads 3 quarks for muster, mark. Zweig called them aces. History went with Gell-Mann's name. The quark model was elegant and powerful. It proposed that all the particles in the zoo could be built from combinations of just a few types of quarks. In its original form, the model had 3 types, or flavors, of quarks: the up quark, the down quark, and the strange quark. Each carried a fractional electric charge, which was revolutionary because every charge ever observed had been a whole multiple of the electron's charge. The up quark carried a charge of positive 2/3. The down quark carried a charge of negative 1/3. A proton was made of 2 up quarks and 1 down quark. The total charge worked out perfectly. 2 times positive 2/3 plus 1 times negative 1/3 equals positive 1. Exactly the charge of a proton. A neutron was made of 1 up quark and 2 down quarks. 1 times positive 2/3 plus 2 times negative 1/3 equals 0. A neutron is electrically neutral, which matched perfectly. The model also explained the masses of the particles, at least approximately. It explained their charges, their spins, their magnetic moments, and how they interacted with each other. It organized the entire particle zoo into a clean, logical framework. But not everyone was convinced. Many physicists treated quarks as a mathematical trick, a useful bookkeeping device rather than real physical objects. After all, no one had ever seen an isolated quark. Every experiment that looked for free quarks roaming around on their own outside of protons and neutrons, came up empty. Quarks, if they existed, were somehow permanently trapped inside larger particles. This was deeply suspicious. How could something be real if you could never isolate it? How could something be fundamental if you could never observe it independently? The decisive experiments came at the Stanford Linear Accelerator Center, known as SLAC, starting in 1967. A team led by Jerome Friedman, Henry Kendall, and Richard Taylor fired extremely high-energy electrons at protons. These electrons had so much energy that their associated wavelength was small enough to probe the internal structure of the proton. In quantum mechanics, particles behave like waves, and the higher a particle's energy, the shorter its wavelength. Short wavelengths can resolve fine details, just like short wavelength light lets you see smaller objects under a microscope. These high-energy electrons were essentially taking snapshots of what was happening inside the proton, resolving details at scales never before accessible. The technique was called deep inelastic scattering. Deep, because the electrons penetrated inside the proton. Inelastic, because the collisions transferred so much energy that the proton was disrupted. And the results were stunning. The electrons weren't scattering off a smooth, uniform blob of matter. They were bouncing off hard, point-like objects inside the proton. The scattering patterns showed unmistakable evidence that the proton contained small, discrete, fractionally charged particles. The patterns were exactly what you would expect if there were tiny, nearly free particles rattling around inside the proton. Quarks were real. They weren't a mathematical fiction or a convenient bookkeeping device. They were actual physical objects inside the proton, carrying exactly the fractional charges that Gell-Mann and Zweig had predicted. Friedman, Kendall, and Taylor won the Nobel Prize in Physics in 1990 for this discovery. It was one of the most important experiments of the 20th century. It proved that the proton, which had been considered a fundamental building block of matter for decades, was itself made of something smaller. The proton had layers. Reality had another floor beneath the one we thought was the basement. But here's where the story takes its most dramatic turn. The quark model was confirmed. Protons were made of quarks. But when physicists measured the masses of the individual quarks and added them up, something deeply unsettling happened. It didn't add up. An up quark has a mass of about 2.2 million electron volts divided by the speed of light squared. I know that units sound strange, but in particle physics, mass is measured in units of energy using Einstein's equation E equals mc squared. The down quark has a mass of about 4.7 million electron volts divided by the speed of light squared. A proton contains 2 up quarks and 1 down quark. So if you add up the quark masses, you get roughly 2.2 plus 2.2 plus 4.7. That's about 9.1 million electron volts divided by the speed of light squared. But the proton's total mass is about 938 million electron volts divided by the speed of light squared. The quarks account for only about 9.1 out of 938. That's less than 1%. The ingredients, the actual particles inside the proton, contribute less than 1% of the proton's mass. This was baffling. Where was the other 99% coming from? If the quarks were almost massless compared to the proton they made up, then the mass of the proton couldn't be coming from the mass of its parts. Something else was generating nearly all of the proton's mass. Something that wasn't a particle in the traditional sense. The proton wasn't just a bag of 3 quarks sitting quietly together. When physicists peered inside it, they found something far more complex, far more violent, far more beautiful, and far stranger than anyone had expected. The inside of a proton wasn't calm and orderly. It was a raging storm, a storm of force and energy, churning and roiling at unimaginable speeds. And that storm, that violent maelstrom of energy confined within less than 1 femtometer of space, was where almost all of the proton's mass was hiding. To understand where that mass comes from, we need to understand the force that creates the storm. The strongest force in the known universe, a force so powerful that it makes gravity look like a gentle breeze by comparison. A force that holds the very fabric of matter together. And a force that breaks every intuitive rule you've ever learned about how the universe works. So the quarks inside the proton barely account for any of its mass. Less than 1%. That's the mystery we left off with. But before we can solve it, we need to understand something even more fundamental. We need to understand why the quarks are stuck inside the proton in the first place, because that turns out to be the key to everything. Think about it. If the proton is made of quarks, why can't we just pull them out? We can pull electrons out of atoms easily enough. That's what happens every time you rub a balloon on your hair and it sticks to the wall. Static electricity is just electrons being transferred from one material to another. So why can't we do the same thing with quarks? Why can't we crack open a proton and extract one? The answer is the strong force. And the strong force is unlike anything else in nature. You already know about some of the fundamental forces. Gravity pulls massive objects toward each other. It's what keeps your feet on the ground, what keeps the Earth orbiting the Sun, what holds galaxies together. Electromagnetism is the force between electrically charged particles. It's what makes magnets work, what powers your phone, what holds atoms together in molecules. These are the forces you experience every day. But there's a third force, one that operates at scales so small you'll never feel it directly. And it's vastly more powerful than either gravity or electromagnetism. This is the strong nuclear force, sometimes just called the strong force. It's the force that holds the nucleus of every atom together, and it's the force that keeps quarks imprisoned inside protons and neutrons. How strong is it? Let's compare. Inside an atom, the electromagnetic force between a proton and an electron is about 10 to the 39th power times stronger than the gravitational attraction between them. Electromagnetism completely dominates gravity at atomic scales. That's why atoms hold together through electromagnetic force rather than gravity. But the strong force is about 100 times stronger than the electromagnetic force at nuclear distances. That means, at the scale of a proton, the strong force overwhelms electromagnetism the same way electromagnetism overwhelms gravity. That makes the strong force roughly 10 to the 41st power times stronger than gravity. It is, by an almost incomprehensible margin, the most powerful force in the known universe. Nothing else comes close. If gravity were a whisper, electromagnetism would be a conversation. The strong force would be a jet engine. But here's what's peculiar. Despite being the strongest force in nature, you've never directly felt it. You've never experienced its pull, never seen its effects in everyday life. And the reason is range. Gravity has infinite range. The sun's gravity reaches across the entire solar system and beyond. Electromagnetism also has infinite range. Light from distant stars travels billions of light years to reach your eyes. But the strong force has an incredibly short range. It only operates over distances of about 1 femtometer, roughly the size of a proton itself. Beyond that distance, the strong force effectively vanishes. It's like a giant who's unbelievably powerful, but can only reach 1 inch in front of him. Within that inch, nothing can resist him. But step 2 inches away and he can't touch you. This extreme short range is why the strong force doesn't affect your daily life, despite being vastly stronger than any other force. It's trapped inside the nucleus, raging at subatomic scales, holding everything together in a space too small for you to ever perceive. Now, every fundamental force in physics has a carrier particle. A particle that mediates the force, that transmits it from one object to another. For electromagnetism, the carrier particle is the photon. When 2 electrons repel each other, they do so by exchanging photons back and forth. You can think of the photons as tiny messengers carrying information about the electromagnetic force between charged particles. For the strong force, the carrier particles are called gluons. The name is exactly what it sounds like. They glue things together. Gluons are the particles that carry the strong force between quarks, binding them inside protons and neutrons. But gluons are radically different from photons in one crucial way, and this difference changes everything about how the strong force behaves. Photons are electrically neutral. They carry the electromagnetic force, but they themselves have no electric charge. A photon doesn't interact with other photons. 2 beams of light can cross each other without affecting each other at all. You see this every time 2 flashlight beams intersect. They pass right through each other. Photons don't feel the electromagnetic force they carry. They're messengers who don't read each other's mail. Gluons are completely different. Gluons carry what's called color charge. This is the strong force equivalent of electric charge, and gluons themselves possess it. This means gluons feel the very force they carry. They interact with each other. They pull on each other. They can even create more gluons. This is as if the postal workers delivering your mail couldn't help but open each other's letters, write responses, and send even more mail. The system becomes incredibly complex because the messengers are part of the conversation. This single fact, that gluons carry color charge and interact with each other, is what makes the strong force so fundamentally different from every other force in physics. and it's what makes the inside of a proton so extraordinarily strange. Now, I need to explain color charge because it's central to everything that happens inside a proton. And I want to be clear from the start, color charge has absolutely nothing to do with actual colors. Quarks aren't red or blue or green. They don't emit light in those wavelengths. Physicists chose the word color as a metaphor because the mathematics of how color charges combine turned out to be analogous to how actual colors of light combine. It's a label, nothing more, but it's a useful label. So let's work with it. In electromagnetism, there's one type of charge, electric charge. It comes in two varieties, positive and negative, like charges repel. Opposite charges attract. That's it. Simple. The strong force is more complicated. Instead of one type of charge with two varieties, there are three types of color charge: red, green, and blue. Each quark carries one of these three color charges at any given moment. But here's where it gets interesting. The strong force requires that any composite particle you can actually observe must be color neutral. Just as atoms prefer to be electrically neutral, with equal amounts of positive and negative charge, particles bound by the strong force must be color neutral. And the way to achieve color neutrality is similar to how you mix colors of light. In optics, if you combine red light, green light, and blue light in equal amounts, you get white light. White is color neutral. It's the absence of any particular color bias. The same principle applies to quarks. A proton contains 3 quarks, one red, one green, and one blue. The 3 colors combine to make the proton color neutral or white, just as 3 colors of light combine to make white light. This is why a proton always has exactly 3 quarks, not 2, not 4, but 3. You need all 3 color charges to cancel each other out. There's another way to be color neutral. You can combine a color with its anti-color, red and anti-red, green and anti-green, blue and anti-blue. Just as positive and negative electric charges cancel, a color and its anti-color cancel. This is how mesons work. Mesons are particles made of one quark and one antiquark. The quark carries a color, and the antiquark carries the corresponding anticolor. The combination is color neutral. Mesons are real particles that show up in high-energy physics experiments all the time. They're unstable, typically living for only tiny fractions of a second before decaying, but they exist and they confirm the color charge theory beautifully. The theory that describes all of this, the complete mathematical framework governing quarks, gluons, and color charge, is called quantum chromodynamics, or QCD. Chromo comes from the Greek word for color. Dynamics refers to how things change and interact. So quantum chromodynamics literally means the quantum theory of color forces. QCD is one of the pillars of the standard model of particle physics, the overarching theory that describes all known fundamental particles and 3 of the 4 fundamental forces. The standard model includes electromagnetism, the weak nuclear force that governs radioactive decay, and the strong force described by QCD. Only gravity remains outside its framework. QCD was developed throughout the 1970s by many physicists, including Murray Gell-Mann, Harold Fritsch, and Heinrich Leutwiler, building on decades of experimental and theoretical work. In QCD, gluons are the carriers of the color force, but unlike photons, which are electrically neutral, gluons carry combinations of color and anticolor. A gluon might carry, for example, a combination of red and anti-blue. When a quark emits a gluon, the quark's color changes. A red quark might emit a red anti-blue gluon and become a blue quark. The gluon then gets absorbed by another quark, changing that quark's color as well. Colors are constantly shifting, constantly being exchanged. The quarks inside a proton are continuously changing color as they exchange gluons, flickering from red to green to blue and back again, millions and millions of times per second. At any given instant, one quark is red, one is green, and one is blue. But which quark has which color is constantly changing? The overall proton remains color neutral at all times, but its internal color configuration is a blur of perpetual change. There are 8 types of gluons in QCD, each carrying a different combination of color and anticolor. 8 messengers, all carrying color charge, all interacting with each other. Compare this to electromagnetism, which has just one type of photon. The strong force is fundamentally more complex. It has more carriers, those carriers interact with each other, and the result is a force that behaves in ways that seem almost impossible. The most dramatic consequence of gluons carrying color charge is a phenomenon called confinement. This is one of the strangest and most important properties of the strong force, and it's something that has no analog in any other force. Confinement means that quarks can never be isolated. You can never, no matter how much energy you use, no matter what technique you try, extract a single quark from a proton and hold it up on its own. Quarks are permanently, irrevocably confined inside composite particles. You cannot have a lone quark. It's not just that we haven't figured out how to do it yet. It's that the laws of physics forbid it. Here's why. Imagine you reach inside a proton with some incredibly powerful pair of tweezers and try to pull one quark away from the other two. As you start pulling the quark, you're stretching the gluon field between it and its partners. The gluon field resists. It pulls back. And here's the crucial part. Unlike the electromagnetic force, which gets weaker as you separate two charged particles, the strong force gets stronger as you pull quarks apart. The further you pull, the harder the gluon field pulls back. The energy stored in the gluon field increases as you stretch it. Imagine a rubber band connecting the quarks. Pull and the band stretches. The further you pull, the more tension in the band, the more energy stored in it. With a real rubber band, at some point it would snap and the two pieces would fly apart. Something similar happens with the gluon field, but with a twist that changes everything. As you keep pulling and pumping more and more energy into the gluon field between the quarks, the energy in that field eventually becomes so enormous that something remarkable happens. The energy converts into matter. Einstein's equation, E equals mc squared, works in both directions. Not only can mass be converted into energy, but energy can be converted into mass. When the energy in the stretched gluon field reaches a high enough value, it spontaneously creates a new quark-antiquark pair out of the vacuum. The stretched field snaps, but instead of getting a free quark, you get a new pair of particles that immediately combine with the original quarks to form new composite particles. You start with one proton and try to pull out a quark. You end up with a proton and a meson, or some other combination of color-neutral particles. The quark you were trying to free is still trapped, just in a new arrangement. You can't win. No matter how hard you pull, no matter how much energy you use, the strong force will always generate new quarks to prevent any quark from being alone. This has been tested experimentally thousands of times at particle accelerators around the world. At CERN in Geneva, at Fermilab near Chicago, at Brookhaven on Long Island, at Die TUSW in Hamburg. Every time physicists smash protons together at enormous energies, jets of particles spray out, hundreds, sometimes thousands of particles in a single collision. But every single particle in those jets is color neutral. Every one. Quarks are never seen alone. Not once in the entire history of particle physics has an isolated quark been observed. They always come in groups of 3, forming particles like protons and neutrons, which physicists call baryons. Or they come in quark-antiquark pairs, forming mesons. Confinement is absolute. It is one of the most rigorously tested predictions in all of physics. This is profoundly different from anything you encounter in everyday life. In electromagnetism, you can isolate positive and negative charges easily. You can have a proton sitting by itself with a positive charge or an electron sitting by itself with a negative charge. No problem. But you cannot have a quark sitting by itself with a color charge. The universe simply doesn't allow it. Now here's where the story gets even more counterintuitive. There's a flip side to confinement called asymptotic freedom, and it was one of the most surprising discoveries in the history of physics. Think about how most forces work. Gravity gets weaker as objects move apart. The Earth pulls on you strongly because you're standing on its surface. But fly to the moon and the Earth's pull is much weaker. The same is true for electromagnetism. The force between 2 charged particles gets weaker as they move apart. This makes intuitive sense. The further apart 2 things are, the weaker the force between them. But the strong force does the exact opposite at short distances. At very short distances, at distances much smaller than the size of a proton, quarks barely feel the strong force at all. They move around almost freely, as if they were independent particles with no connection to each other. The closer quarks are to each other, the weaker the strong force becomes. This is asymptotic freedom. The force that binds quarks becomes asymptotically, meaning gradually approaching 0 as the quarks get closer together. This is completely backwards from what you'd expect. It's the opposite of every other force in nature. This discovery was made in 1973 by David Gross and Frank Wilczek at Princeton University and independently by David Politzer at Harvard. They showed mathematically that the strong force weakens at short distances and strengthens at large distances. This was the opposite of what everyone expected. Most physicists assumed that force-carrying particles that interacted with each other would make the force stronger at short distances, not weaker. Gross, Wilczek, and Politzer showed that the peculiar mathematical structure of QCD, specifically the self-interaction of gluons, produces this counterintuitive behavior. Their calculation was a tour de force of theoretical physics, one of the most important results in the field since Einstein's work on general relativity. It earned them the Nobel Prize in Physics in 2004, and it explained one of the deepest mysteries of the strong force: how quarks can appear free when probed at close range yet remain permanently trapped when you try to separate them. Asymptotic freedom explains what the SLAC experiment saw. When Friedman, Kendall, and Taylor fired extremely high-energy electrons at protons, those electrons had wavelengths short enough to probe the interior of the proton at very close range. At those tiny distances, the quarks were behaving almost as free particles because the strong force was weak. The electrons bounced off the quarks as if the quarks were just sitting there independently, not bound to anything. This made it possible to see the quarks clearly and measure their properties. If the strong force had been equally strong at all distances, the quarks would have been smeared out and inseparable, and the experiments wouldn't have revealed the clear point-like scattering that they found. But here's the paradox. The same quarks that look almost free when probed at very short distances are permanently confined when you try to separate them to larger distances. The strong force is weak close up and overwhelmingly powerful far away. It's like a trap that lets you wander freely in a very small room, but makes the walls absolutely impossible to break through. This strange combination of asymptotic freedom and confinement creates something truly extraordinary inside the proton. And this is where the picture most people have of a proton falls apart completely. Because the inside of a proton is nothing like the simple diagram you see in textbooks. Most textbook illustrations show a proton as three little spheres sitting placidly inside a larger circle. Two up quarks and a down quark, neatly arranged, maybe with a few wavy lines between them to suggest some kind of connection. It looks static, calm, orderly, three balls in a bag. This picture is not just wrong, it's catastrophically misleading. The real interior of a proton is a maelstrom, a churning, seething, boiling storm of particles and energy that never stops, never slows down, never reaches equilibrium. The three quarks that give the proton its identity, the two up quarks and one down quark, are called valence quarks. They're the permanent residents, but they're not alone in there. Not even close. The gluon field inside the proton is so energetic, so intensely active, that it constantly creates pairs of quarks and antiquarks out of pure energy. A gluon splits into a quark and an antiquark. Those exist for an incredibly brief moment, then annihilate each other back into a gluon. Or the gluon they create splits again. Or they interact with the valence quarks. Or they exchange gluons with other particles. This is happening constantly, everywhere inside the proton, at all times. These temporary quark-antiquark pairs are called C-quarks. They're not permanent residents like the valence quarks. They flash into existence and vanish again almost instantly. But there are always some present at any given moment. The proton is filled with them, swarming in and out of existence like fireflies blinking on and off in the darkness. And the gluons themselves are even more numerous. Gluons are constantly being emitted and absorbed by the quarks. But because gluons carry color charge, they also interact with each other. A gluon can emit another gluon. Two gluons can scatter off each other. A gluon can split into two gluons. The gluon field is self-interacting, constantly generating more of itself in a roiling cascade of creation and annihilation. Here's a number that captures how complex this really is. When the SLAC experiments probed the proton's interior, they found that the three valence quarks carried only about half of the proton's total momentum. Half. The other half was carried by something that didn't have electric charge, something the electrons couldn't scatter off directly. That something was the gluons. Half of the proton's momentum, half of its internal activity, belongs to the gluon field. The quarks, the particles that supposedly make up the proton, carry only about half of its momentum. The gluons, the force carriers that were supposed to just be the glue holding things together, carry just as much. Further experiments at higher energies revealed even more detail. The C quarks also carry a portion of the proton's momentum. When you add up all the contributions, the picture that emerges is this. At any given instant, a proton might contain its 3 valence quarks, plus several C quark antiquark pairs, plus dozens or hundreds of gluons, all moving at speeds close to the speed of light, all packed into a space less than 1 femtometer across. The proton is not 3 quarks. It's 3 quarks plus a vast entourage of temporary particles, all bound together by the most powerful force in the universe. The number of particles inside a proton isn't even fixed. It depends on the energy at which you probe it. Look at the proton with low energy probes, and you see mostly the 3 valence quarks. Look at it with higher energy probes, which means looking at finer detail, and you start to see the C quarks and gluons. Look at it with even higher energy, and you see more and more particles. It's as if the proton has layers of complexity that reveal themselves the closer you look. At each new scale, there's more going on than you expected. More particles, more interactions, more energy. The proton is not a simple object. It's one of the most complex systems in all of physics. The theoretical framework that ascribes all of this, quantum chromodynamics, is one of the most mathematically challenging theories ever devised. It's so complex that for most problems, we cannot solve the equations exactly. The self-interaction of gluons, the constant creation and annihilation of C quarks, the shifting of color charges, all of this creates a mathematical nightmare. The equations of QCD are known and believed to be correct, but actually solving them for a system as complex as a proton is extraordinarily difficult. This is where computers come in. Physicists have developed a technique called lattice QCD, where they model space-time as a discrete grid of points, a lattice, and calculate the behavior of quarks and gluons on this grid using powerful supercomputers. Lattice QCD calculations are among the most demanding computations in all of science. They require massive amounts of processing power and can take months or even years to complete, but they work. Lattice QCD has successfully predicted the masses of protons, neutrons, and other particles from the fundamental equations of the strong force. We'll explore these calculations more shortly because they're the key to solving our central mystery. Let me paint one more picture of the proton's interior because I want you to really feel how different it is from the clean textbook image. Imagine you could somehow shrink yourself down and hover at the boundary of a proton, looking in. What you would see wouldn't resemble anything in your everyday experience. It would be more like staring into the heart of a hurricane made of pure energy. Quarks whipping around at nearly the speed of light, changing direction as gluons slam into them. Gluons stretching between quarks like blazing threads of force, then splitting, multiplying, recombining. Quark-antiquark pairs erupting out of the gluon field and vanishing again in an instant. The entire volume seething with activity. Every cubic femtometer packed with more energy and more particles than the space outside the proton would ever contain. There is no stillness inside a proton, no calm center, no quiet corner. It's violence all the way down. A contained explosion that has been raging for the entire history of the universe, and will continue raging for a time so long it might as well be forever. And here's the astonishing part. This storm of particles and energy is not just what's happening inside the proton. In a very real sense, this storm is the proton. The proton is not a container that holds quarks and gluons. The proton is the quarks and gluons and the force between them and the energy of that force and the sea of virtual particles that the force creates. All of it together, all of it at once, inextricable, inseparable, constituting a single bound system that we call a proton. And this brings us back to the puzzle that started this entire investigation: the mass. The 3 valence quarks, the permanent residents inside this maelstrom, have a combined intrinsic mass that accounts for less than 1% of the proton's total mass. So, where is the other 99% coming from? The answer is staring us in the face. It's the storm. It's all that energy. The gluons flying around at nearly the speed of light. The sea quarks flashing in and out of existence. The kinetic energy of the valence quarks as they zip back and forth inside their tiny prison. The potential energy stored in the gluon field as it stretches and compresses between the quarks. All of that energy, the energy of the strong force itself, is where the proton's mass comes from. And the bridge between energy and mass, the equation that makes this possible, is the most famous equation in all of physics. An equation written by a Parton clerk in Bern, Switzerland, in the year 1905. An equation so simple a child can memorize it, yet so profound it rewrote our understanding of what matter actually is. E equals mc squared. 5 symbols. Probably the most recognized equation in human history. People who have never taken a physics class in their life know this equation. They've seen it on t-shirts, coffee mugs, posters, bumper stickers. It's become a cultural icon, a shorthand for genius itself, forever associated with the wild-haired figure of Albert Einstein. But here's the strange thing. Most people who recognize the equation have no idea what it actually means. They know it's important. They know it has something to do with energy and mass. They might vaguely associate it with the nuclear weapons or nuclear power, but the true meaning of E equals mc squared, what it really tells us about the nature of reality, is something most people have never been told. And it's far more profound than almost anyone realizes. Because this equation doesn't just describe nuclear bombs, it describes you. It describes every atom in your body. It describes the ground beneath your feet and the air you're breathing and the stars in the sky. It tells us that mass and energy are the same thing. Not similar, not related, not connected in some abstract mathematical sense. The same thing. 2 faces of one coin, 2 manifestations of a single underlying reality. Einstein published this insight in 1905 as part of his special theory of relativity. He was 26 years old, working as a patent clerk in Bern, Switzerland, examining other people's inventions during the day and revolutionizing physics in his spare time. 1905 is sometimes called Einstein's miracle year because he published 4 groundbreaking papers that year, any one of which would have secured his place in the history of science. The paper on mass energy equivalence was just 3 pages long, 3 pages that changed our understanding of reality forever. In it, he showed that the energy contained in a body at rest is equal to its mass multiplied by the speed of light squared. The speed of light is about 300 million meters per second. When you square that number, you get 9 times 10 to the 16th power. That's 90 quadrillion. So even a tiny amount of mass corresponds to an enormous amount of energy. A single kilogram of matter, if you could convert it entirely into energy, would release about 90 quadrillion joules. That's roughly equivalent to the energy released by 21 megatons of TNT, about 1,400 times the energy of the atomic bomb dropped on Hiroshima. From 1 kilogram, 1 bag of sugar. That small bag sitting in your kitchen contains enough energy to power a major city for days if you could convert all of its mass into energy. That's the power of c squared. It's an enormous conversion factor that tells us mass is an incredibly concentrated form of energy. Energy packed so tightly that we perceive it as solid, tangible matter. But Einstein's equation works in both directions. This is the part most people miss. Not only can mass be converted into energy, which is what happens in nuclear reactions, but energy can manifest as mass. If you have enough energy concentrated in a small enough space, that energy will have mass. It will be heavy. It will resist acceleration. It will respond to gravity. Not because there's stuff there in the traditional sense, not because there are particles with inherent weight, but because energy itself has mass. Energy curves space-time. Energy has inertia. Energy weighs something. Let me say that again because it's the key to everything we're about to discuss. Energy has mass. Not metaphorically, not approximately, not in some hand-wavy poetic sense, literally, physically, measurably. If you take a sealed, perfectly reflective box and fill it with light, with photons bouncing around inside it, that box will weigh more than an identical empty box. The photons themselves are massless. Individual photons have no rest mass at all. They are pure energy traveling at the speed of light. But the energy they carry contributes to the mass of the system that contains them. The box with light inside it is heavier than the box without light inside it. If you could measure precisely enough, you would detect this additional weight. Similarly, if you heat up an object, it becomes very slightly heavier. Not because you've added atoms, but because you've added thermal energy to the atoms that are already there. And that energy has mass. This has been confirmed experimentally through precision measurements. It's not speculation or extrapolation, it's measured, verified physical fact. Now let's apply this to the proton. We established that a proton contains 3 valence quarks, 2 up quarks and 1 down quark, plus a churning sea of gluons and virtual quark-antiquark pairs. The 3 valence quarks have intrinsic masses. These are the masses that the quarks would have if you could somehow isolate them and weigh them individually, which you can't because of confinement, but which can be determined through careful analysis of experimental data and theoretical calculations. The up quark has an intrinsic mass of about 2.2 million electron volts divided by c squared. The down quark has an intrinsic mass of about 4.7 million electron volts divided by c squared. Those units might sound unfamiliar, so let me explain. In particle physics, mass is measured in units of energy divided by the speed of light squared, which comes directly from E equals mc squared. If you rearrange the equation, m equals E divided by c squared. So instead of measuring mass in kilograms, which would give absurdly small numbers for particles, physicists measure it in energy units. 1 million electron volts, or 1 mega electron volt, is a convenient unit of energy at the subatomic scale. It's the amount of energy an electron gains when accelerated through an electric potential of 1 million volts. So, 2-up quarks at 2.2 mega electron volts each gives 4.4 mega electron volts. 1 down quark at 4.7 mega electron volts gives 4.7 mega electron volts. Add them together and you get about 9.1 mega electron volts. That's the total intrinsic mass of all 3 valence quarks inside the proton. But the proton's measured mass is 938 mega electron volts. 9.1 out of 938. The quarks, the actual particles inside the proton, account for less than 1% of its mass. About 0.97% to be more precise, less than 1%. The quarks are almost nothing. They're like 3 raisins in a cake that weighs 100 times more than the raisins alone. The cake isn't made of raisins. It's made of something else. And the proton isn't made of quark mass. It's made of something else too. Where do those tiny intrinsic quark masses come from in the first place? This is where the Higgs field enters the story. And I want to be very precise here because the Higgs field is one of the most misunderstood concepts in popular science. It's been the subject of more misleading headlines and oversimplified explanations than almost any other topic in physics. Most people think the Higgs field is what gives everything its mass. You'll hear people call the Higgs boson, the God particle, a term that most physicists actually dislike, and say things like the Higgs field is responsible for all mass in the universe. This is not correct. It's a dramatic oversimplification that misses the most important and most fascinating part of the story. In 1964, several physicists independently proposed a mechanism to explain why certain fundamental particles have mass while others don't. Peter Higgs in Edinburgh, Robert Brout and François Englert in Brussels, and Gerald Guralnik, Carl Hagen, and Tom Kibble in London all published papers describing versions of this mechanism within a short period of each other. The idea, which became known as the Higgs mechanism, proposes that a quantum field permeates all of space. Every point in the universe, every cubic centimeter of vacuum is filled with this field. You can't see it. You can't feel it directly. But it's there, everywhere, at all times. Fundamental particles interact with this field as they move through it. The strength of a particle's interaction with the Higgs field determines how much intrinsic mass it acquires. Particles that interact strongly with the Higgs field are heavy. Particles that interact weakly with the Higgs field are light. Particles that don't interact with the Higgs field at all, like photons, are massless. Think of it like walking through a room full of people at a crowded party. If you're a famous celebrity, everyone wants to stop and talk to you. They crowd around you, slow you down, make it hard for you to change direction. You acquire a kind of inertia, a resistance to motion, that has nothing to do with your physical size. That's like a heavy particle interacting strongly with the Higgs field. The top quark, for example, couples very strongly to the Higgs field, which is why it has such an enormous mass. If you're unknown, nobody pays attention. You walk through the room easily, barely noticing the crowd. That's like a light particle interacting weakly with the Higgs field. The electron and the up and down quarks interact weakly with the Higgs field, which is why their intrinsic masses are small. And if you're completely invisible, nobody even notices you're there. You pass through the crowd unimpeded, as if the room were empty. That's like a photon, which doesn't interact with the Higgs field at all, and therefore has no intrinsic mass, and always travels at the speed of light. The Higgs mechanism was confirmed spectacularly in 2012 when the ATLAS and CMS experiments at the Large Hadron Collider at CERN, the European Organization for Nuclear Research in Geneva, Switzerland, announced the discovery of the Higgs boson. The Higgs boson is the quantum excitation of the Higgs field, the particle associated with the field, just as a photon is the quantum excitation of the electromagnetic field. Finding the Higgs boson confirmed that the Higgs field exists and that the mechanism works. Peter Higgs and François Englert were awarded the Nobel Prize in Physics in 2013. Robert Brute had passed away in 2011 and sadly could not share in the prize. Now, here's the crucial point that most popular accounts get wrong. The Higgs field gives fundamental particles their intrinsic rest mass. It explains why the electron has a mass of 0.511 mega electron volts, why the up quark has a mass of about 2.2 mega electron volts, why the down quark has a mass of about 4.7 mega electron volts, and why the top quark, the heaviest known fundamental particle, has a mass of about 173,000 mega electron volts, which is roughly the mass of an entire gold atom packed into a single point-like particle. The Higgs field sets these intrinsic masses. Without it, all fundamental particles will be massless and would travel at the speed of light, just as photons do. Without the Higgs field, atoms couldn't form. Chemistry couldn't exist. The universe would be a completely different place. But here is what the Higgs field does not do. It does not account for most of the mass you experience in everyday life. The Higgs field gives the up quark a mass of 2.2 mega electron volts. It gives the down quark a mass of 4.7 mega electron volts. These are the intrinsic masses of the quarks set by their coupling to the Higgs field. And when you add up these intrinsic quark masses inside a proton, you get about 9.1 mega electron volts out of a total proton mass of 938 million electron volts. The Higgs field is responsible for less than 1% of the proton's mass. Since protons and neutrons make up nearly all the mass of every atom, and since atoms make up all ordinary matter, this means the Higgs field is responsible for less than 1% of the mass of everything you see around you. Less than 1% of your body weight. Less than 1% of the mass of the Earth. Less than 1% of the mass of the Sun. The Higgs field is critically important for giving fundamental particles their intrinsic masses, and without it the universe would be unrecognizable. But it's not the primary source of the mass you experience every day. Not even close. So where does the other 99% come from? We've been building toward this answer for the entire journey, and now it's time to state it clearly. The remaining 99% of the proton's mass comes from the energy of the strong force. Specifically, it comes from 3 sources of energy inside the proton, all related to the storm of quarks and gluons we described earlier. First, there's kinetic energy. The valence quarks inside the proton are not sitting still. They're moving at velocities close to the speed of light, bouncing around inside their femtometer-sized prison, confined by the strong force that won't let them escape. These quarks have enormous kinetic energy, and according to E=mc², that kinetic energy contributes to the proton's mass. Moving quarks are heavier than stationary quarks would be, not because they've gained more stuff, but because their energy of motion manifests as mass. Second, there's the energy of the gluon field itself. The gluons inside the proton are not just passive connectors between quarks. They're energetic particles in their own right, flying around at the speed of light, since gluons, like photons, are massless particles that always travel at light speed. The gluon field contains enormous energy. Gluons are constantly being emitted and absorbed, splitting and recombining, interacting with each other in a never-ending cascade. All of this activity represents energy, and that energy, via E equals mc squared, manifests as mass. Remember that roughly half the proton's momentum is carried by gluons. These massless particles contribute roughly half of the proton's mass through their energy alone. Third, there's the energy associated with the creation and annihilation of C-quark antiquark pairs. The gluon field is so energetic that it constantly produces virtual quark antiquark pairs that flash into existence and vanish again. These virtual particles carry energy during their brief lives, and that energy also contributes to the proton's overall mass. All three of these contributions are forms of energy stored in the strong interaction field inside the proton. The kinetic energy of quarks and gluons, the potential energy of the gluon field, the energy associated with virtual particle creation. None of this is intrinsic particle mass in the sense that the Higgs field creates. It's energy, pure energy, trapped inside a femtometer-sized volume by the confinement property of the strong force. And that trapped energy, through Einstein's E equals mc squared, is what we experience as mass. When you step on a scale, the number you see is almost entirely a measure of strong force energy locked inside the protons and neutrons in your atoms. Not Higgs mass, not the intrinsic weight of fundamental particles. Energy, bound, confined, concentrated energy. Let me be very clear about the distinction because it's the most important point in this entire story. There are two separate sources of mass at work inside the proton. The first source is the Higgs field. The Higgs field gives quarks their intrinsic rest mass. This is a property each quark has simply by virtue of existing. An up quark has a mass of 2.2 mega electron volts because of how strongly it couples to the Higgs field. A down quark has a mass of 4.7 mega electron volts for the same reason. This mass is intrinsic. It's a fundamental property of the particle itself. The second source is the energy of the strong interaction field, manifesting as mass through E equals mc squared. This is not intrinsic to any particle. It's a property of the system as a whole, an emergent property that arises from the dynamics of the strong force, from quarks and gluons moving and interacting within the confined space of the proton. It's sometimes loosely called binding energy, though it works very differently from the binding energy in atoms or nuclei that you might have learned about in chemistry class. In an atom, the binding energy is actually negative, meaning the bound system weighs slightly less than its separated parts. A hydrogen atom weighs very slightly less than a free proton plus a free electron because some energy was released when they combined. You'd need to put that energy back in to tear them apart, but in the proton, the situation is dramatically reversed. The strong force energy is positive and enormous, making the bound system weigh vastly more than its parts. The proton is heavier than its ingredients, not lighter. The energy of the interactions adds mass rather than subtracting it. This is a profound inversion of what most people expect. In everyday life, we assume that a whole is the sum of its parts. If you have a bag containing 3 oranges, the bag weighs roughly the combined weight of the 3 oranges. A house weighs roughly the combined weight of its bricks and lumber and concrete. A car weighs the sum of its engine, its frame, its seats, its tires. Things weigh what their components weigh. But at the subatomic level, this intuition catastrophically fails. The proton weighs roughly 100 times more than the combined weight of the quarks inside it. The whole is vastly heavier than the sum of its parts. The extra mass comes from the energy of the interactions between the parts. It comes from the force that connects them. Now, you might reasonably ask how we know all this is correct. How can we be sure that the strong force energy really does account for the proton's mass? Maybe there's something else going on. Maybe there are other particles inside the proton we haven't discovered yet. Maybe our understanding of the strong force is incomplete. These are fair questions. And the answer comes from one of the most impressive achievements in the history of computational physics: lattice QCD. Remember that quantum chromodynamics, QCD, is the theory describing the strong force. Its equations are known. They describe how quarks and gluons interact with each other through color charge. In principle, you should be able to take these equations, plug in the known properties of quarks and gluons, and calculate the mass of the proton from scratch. In practice, this is extraordinarily difficult. The equations of QCD are so complex that they cannot be solved with pen and paper. The self-interaction of gluons, the constant creation of virtual particles, the shifting color charges, all of this makes the mathematics intractable using standard analytical techniques. So physicists turned to computers. In the 1970s and 80s, a technique called lattice QCD was developed, pioneered by physicist Kenneth Wilson, who won the Nobel Prize in Physics in 1982 for related work on phase transitions. The idea is to represent space-time not as a smooth continuum, but as a discrete grid of points, a lattice. You place quarks on the lattice points and gluon fields on the links between them. Then you use the equations of QCD to calculate how the quarks and gluons interact on this lattice, step by step, point by point. By making the lattice spacing smaller and smaller, you can approximate the behavior of the real continuous system with increasing accuracy. This sounds straightforward in principle, but in practice it requires staggering amounts of computational power. The difficulty arises because the strong force is inherently non-linear and self-interacting. You can't simplify the problem. You can't take shortcuts. You have to calculate every interaction. A typical lattice QCD calculation might involve a grid of 32 points in each of the 4 dimensions of space-time. 3 spatial dimensions plus time. That's over 1 million lattice points. At each point, you need to track the quark and gluon fields, each with multiple components reflecting the color charges and spin states. The calculations involve generating thousands of random field configurations using sophisticated statistical methods, computing physical quantities for each one, and averaging over all of them using techniques borrowed from statistical mechanics. A single high-precision lattice QCD calculation can take months of continuous running on some of the world's most powerful supercomputers. These machines perform quadrillions of floating point operations per second, and lattice QCD pushes them to their absolute limits. But the results are spectacular. In 2008, a collaboration of physicists led by Stefan Dürr and their colleagues at multiple institutions across Europe and the United States published a landmark paper in the journal Science. They had performed the most precise lattice QCD calculation of the proton mass ever done. Starting from nothing but the fundamental equations of QCD and the known quark masses, which are inputs from the Higgs mechanism, they calculated the mass of the proton entirely from first principles. No fitting, no fudge factors, no adjustable parameters beyond what was already measured independently. Just the raw equations of the strong force, solved numerically on a supercomputer. They also calculated the masses of other particles made of quarks, including the neutron, the kaon, and various other mesons and baryons. Their results agreed with the experimentally measured masses to within a few percent. The proton mass came out right. The neutron mass came out right. Particle after particle, the calculations matched the measurements beautifully. This was a triumph. It confirmed that QCD is the correct theory of the strong force. It confirmed that the strong force energy is indeed responsible for the vast majority of the proton's mass. And it showed that you can start with essentially massless quarks and nearly massless gluons, let the strong force do its work, and end up with a proton that weighs roughly 100 times more than its ingredients. The mass appears from the energy of the interactions. E equals AIC squared, made manifest in the most dramatic way possible. Since that landmark calculation, lattice QCD has continued to improve. Modern calculations agree with measured particle masses to better than 1% precision in many cases. The technique has been used to predict the masses of particles before they were discovered, experimentally, and to calculate quantities that are extremely difficult to measure directly. Lattice QCD is not a toy model or an approximation. It's a rigorous, first principles calculation that directly connects the fundamental theory to observable reality. So let's summarize where we stand. The proton's mass is 938 mega electron volts. Of that total, about 9 mega electron volts comes from the intrinsic masses of the 3 valence quarks, masses that are set by the Higgs field through each quark's coupling to it. The remaining roughly 929 mega electron volts comes from the energy of the strong interaction field inside the proton. This energy has 3 major components: the kinetic energy of quarks moving at near light speeds, the energy of the gluon field carried by massless gluons flying around at the speed of light and constantly interacting with each other and the quarks, and the energy associated with virtual C quark antiquark pairs flashing in and out of existence. All of this energy, via Einstein's E equals mc squared, manifests as mass, real, measurable, gravitating mass, the kind of mass that makes the proton heavy, that gives atoms their weight, that holds the universe together. 2 completely different mechanisms, working together, creating what we experience as the mass of matter. The Higgs field provides the small intrinsic masses of fundamental particles. The strong force provides the overwhelming majority of the mass of composite particles like protons and neutrons. If you could somehow switch off the strong force energy while leaving everything else intact, the proton would lose 99% of its mass. You would lose 99% of your mass. The Earth, the Sun, the stars, everything made of ordinary matter would become almost weightless. Not because the atoms disappeared, but because the energy that gives them their heft. The energy of the strongest force in nature raging inside every proton and every neutron would be gone. The Higgs boson was called the God particle in popular media. It made headlines around the world when it was discovered in 2012, and its discovery was genuinely important. It confirmed a prediction that was nearly 50 years old and validated a crucial piece of the Standard Model. But in terms of where your mass actually comes from, in terms of what makes you weigh what you weigh, the Higgs field is a minor player. The real source of mass, the mechanism that generates the overwhelming majority of the mass of everything in the visible universe, is far less famous. It's the energy of the strong force, the contained fury of quarks and gluons trapped inside protons and neutrons by the most powerful force in nature. It doesn't have a catchy nickname. It didn't get a best-selling book title. But it's the reason you have weight. It's the reason stars can form. It's the reason planets can hold atmospheres, and oceans can fill basins, and your feet stay on the ground when you walk. You are not made of stuff in the way you think. You are made of energy. Bound energy. Trapped energy. Energy that has been masquerading as matter since the first protons formed in the infant universe. And the equation that makes this possible, E equals mc squared, is not just a formula for nuclear bombs. It's the formula for you. Now let's take everything we've learned and turn it outward. Because the proton isn't just an interesting physics curiosity. The proton is you. It's me. It's the chair you're sitting in, the floor beneath you, the walls around you, the air you're breathing, the food you ate today, the planet under your feet, the sun overhead, every star in the sky. The proton and its close, relative the neutron, make up virtually all the mass of every atom in existence. And what's true of the proton is true of you. Let's start with the neutron, because it has the same story with one small but incredibly important twist. A neutron is made of one up quark and two down quarks. That's the reverse of the proton, which has two up quarks and one down quark. The intrinsic masses of the neutron's quarks add up to about 11.6 mega electron volts. One up quark at 2.2 mega electron volts, plus two down quarks at 4.7 mega electron volts each. The neutron's total measured mass is about 939.6 mega electron volts. So once again, the intrinsic quark masses account for barely more than 1% of the total. The rest, about 99%, is energy from the strong force. The same storm, the same mechanism, the same equation. E equals mc squared, turning the fury of the strong interaction into measurable, gravitating mass. But the neutron is slightly heavier than the proton. The neutron's mass is 939.6 mega electron volts compared to the proton's 938.3 mega electron volts. A difference of about 1.3 mega electron volts. That might seem trivially small. It's about 1/10 of 1%. Barely anything. But this tiny difference is one of the most consequential numbers in all of physics. It's one of the reasons you exist. Where does this mass difference come from? Two sources. First, the down quark is slightly heavier than the up quark. The down quark has an intrinsic mass of about 4.7 mega electron volts, while the up quark is about 2.2 mega electron volts. Since the neutron has two down quarks and only one up quark, while the proton has two up quarks and only one down quark, the neutron has slightly more intrinsic quark mass. Second, there are small differences in the electromagnetic energy inside the two particles. The proton contains two positively charged up quarks that repel each other, which adds a small amount of electromagnetic energy. The neutron's charge distribution is different. When you work out all the contributions carefully, including both the quark mass differences set by the Higgs field and the electromagnetic energy differences, the neutron ends up about 1.3 mega electron volts heavier than the proton. This tiny mass difference means that a free neutron, one that isn't safely tucked inside an atomic nucleus, stabilized by the strong force, is unstable. It will spontaneously decay into a proton, an electron, and an anti-neutrino through the weak nuclear force, with an average lifetime of about 14 minutes and 39 seconds. This process is called beta decay. It happens because nature always seeks lower energy states. The neutron has slightly more mass than the proton, which means it has slightly more energy via E equals mc squared. It can shed that extra energy by converting into the lighter proton and releasing the difference as the kinetic energy of the decay products. A free proton, being lighter, cannot decay into a neutron because that would require gaining energy from nowhere, which violates the conservation of energy. This asymmetry between proton and neutron stability is essential for the existence of atoms, chemistry, and life. Inside atomic nuclei, neutrons are stabilized by the nuclear binding energy. The strong force holds protons and neutrons together so tightly that the neutron's slight extra mass is compensated by the energy of the bonds. But the fact that free neutrons decay while free protons don't means that the universe's ordinary matter ended up being dominated by protons, which form the nuclei of hydrogen atoms. Hydrogen is the simplest element, one proton, one electron, and hydrogen is the most abundant element in the universe by far, making up about 75% of all ordinary matter. Stars are mostly hydrogen. They form from clouds of hydrogen gas that collapse under gravity and ignite nuclear fusion at their cores. If neutrons were lighter than protons instead of heavier, the situation would be reversed. Free protons would decay into neutrons. The universe would be filled with free neutrons instead of hydrogen atoms. Neutrons don't form atoms because they have no electric charge. There would be no chemistry, no stars as we know them. No planets, no water, no organic molecules, no life. The fact that you exist is partly a consequence of the down quark being about 2.5 mega electron volts, heavier than the up quark, which is determined by how each quark couples to the Higgs field. Change that coupling by a small amount and the mass difference between protons and neutrons shifts, potentially making protons heavier than neutrons, and the entire universe becomes a lifeless sea of neutrons. The Higgs field may contribute less than 1% of your mass, but the specific values it assigns to quark masses are critically important for whether a universe can support complexity and life. Now, let's extend this to your body. A typical human body contains about 7 billion atoms. That's 7 times 10 to the 27th power. Most of these are hydrogen, oxygen, and carbon, with smaller amounts of nitrogen, calcium, phosphorus, and many other elements. The electrons in all those atoms contribute almost nothing to your mass because electrons are extremely light. An electron's mass is only about 1/1836th of a proton's mass. Virtually all of your body's mass comes from the protons and neutrons in the nuclei of your atoms. And we've established that roughly 99% of each proton's mass and each neutron's mass comes from the energy of the strong force, not from the intrinsic masses of quarks set by the Higgs field. This means roughly 99% of your body mass is energy. Strong force energy. The energy of quarks flying at nearly the speed of light inside their femtometer-sized prisons. The energy of gluons blazing back and forth at the speed of light. The energy of virtual quark-antiquark pairs erupting from the vacuum and vanishing again. All of it trapped inside the protons and neutrons in your atoms, manifesting as mass through E equals mc squared. When you step on a bathroom scale, the number you see is almost entirely a measurement of strong force energy. If you weigh 70 kilograms, about 69.3 kilograms of that is energy from the strong interaction. The Higgs field contributes roughly 700 grams, less than the weight of a bottle of water. That's it. Everything else, the vast overwhelming majority of what makes you heavy, what pulls you toward the earth, what gives your body its resistance to acceleration, is energy, not stuff in the way you intuitively think of stuff. Not some fundamental substance with inherent weight. Energy. Trapped, bound, concentrated energy. This applies to everything, not just human bodies. The Earth has a mass of about 6 times 10 to the 24 kilograms. Roughly 99% of that, about 5.94 times 10 to the 24 kilograms, is strong force energy locked inside the protons and neutrons of its atoms. The rock you might pick up in your garden is mostly energy. The water you drink is mostly energy. The iron core of the Earth is mostly energy. The Sun, which has a mass of about 2 times 10 to the 30 kilograms, is overwhelmingly strong force energy. Every star in the sky, every planet, every moon, every asteroid, every grain of dust floating in interstellar space. All of it is mostly energy masquerading as matter. Think about what this means for how we understand solidity, substance, the feeling of touching something real. We started this journey by touching a table and noting how solid it felt. Now we know that the table is overwhelmingly empty space. The atoms that make it up are more than 99.9999% void. And the tiny fraction that isn't empty, the protons and neutrons in the nuclei of those atoms, is itself 99% energy rather than intrinsic particle mass. The stuff you think of as solid matter is really energy fields interacting with other energy fields across mostly empty space. The sensation of solidity is an electromagnetic illusion created by electron clouds repelling each other. There is nothing solid in the way your brain interprets it. Nothing. Not a table, not a rock, not your own bones. The entire material world is a construction of forces and energy arranged in patterns that your nervous system interprets as substance. This is not philosophy or metaphor. This is measured, verified, experimentally confirmed physics. The mass of the proton has been measured to extraordinary precision. The masses of the quarks have been determined through decades of careful experiments. Lattice QCD calculations have confirmed that the strong force energy accounts for the vast majority of the proton's mass. Every link in this chain has been tested and verified. The conclusion that you are mostly energy is as solid as any fact in science. Let's now connect this to the broader cosmos, because the energy inside protons and neutrons doesn't just sit there inertly. It plays an active role in how the universe works. Stars, including our sun, are powered by nuclear fusion. In the sun's core, where temperatures reach about 15 million degrees and pressures are about 250 billion times Earth's atmospheric pressure, hydrogen nuclei, which are single protons, are forced together so tightly that they overcome their electromagnetic repulsion and fuse into helium nuclei. Each helium nucleus contains 2 protons and 2 neutrons. Here's where it gets interesting. If you take the mass of 4 separate protons, which is what you start with, and compare it to the mass of 1 helium-4 nucleus, which is what you end up with after fusion, the helium nucleus is lighter. About 0.7% lighter. That missing mass hasn't vanished. It's been converted into energy via E equals mc squared. And that energy is what powers the sun. It radiates outward as light and heat, traveling across 93 million miles of space to warm the Earth, drive our weather, fuel, photosynthesis, and ultimately sustain all life on our planet. But where was that released mass energy stored in the first place? It was stored in the strong interaction field inside the protons. When 4 protons fuse into helium, the strong force rearranges itself. The quarks and gluons inside the original protons reorganize into a new, more tightly bound configuration. In this new configuration, the strong force energy is slightly lower. The difference in energy is released as radiation. So the sunlight hitting your face right now, the warmth you feel on a summer day, the light that lets you see, all of it is ultimately energy that was once locked inside protons as strong force energy. The sun is slowly converting strong force energy into light. It's been doing this for about 4.6 billion years, and will continue for about another 5 billion years before it exhausts the hydrogen in its core. Every star in the night sky is doing the same thing. The universe is filled with trillions upon trillions of natural nuclear reactors, each one converting a tiny fraction of the strong force energy inside protons and neutrons into light and heat. The energy you see when you look up at the stars is energy that was originally trapped inside protons by the strongest force in nature. The stars are slowly unlocking that energy, converting mass into radiation, illuminating the cosmos with the freed energy of the strong force. Now let's go all the way back to the beginning. Because there was a time when protons didn't exist. There was a time before the strong force had trapped energy into these remarkably stable bound states. And that time was the very beginning of the universe. The Big Bang occurred about 13.8 billion years ago. In the first instant, the universe was unimaginably hot and dense. Temperatures were so extreme that the fundamental forces behaved differently than they do today. In the first millionths of a second, the universe was filled with a soup of free quarks and gluons. This state of matter is called a quark-gluon plasma. The temperature was so high, well above 1 trillion degrees, that confinement couldn't hold. Quarks and gluons moved freely, not bound into protons or neutrons. Color charge was everywhere, exposed and unconfined. The strong force was present. Quarks and gluons were interacting furiously, but the temperature was too high for stable bound states to form. It was like trying to build a sandcastle in a hurricane. The materials were there, but the conditions were too violent for any structure to survive. Then, roughly 1 microsecond after the Big Bang, as the universe expanded and cooled, something extraordinary happened. The temperature dropped below the critical threshold, about 2 trillion degrees, and the quarks and gluons suddenly condensed into protons and neutrons. This is called the QCD phase transition, and it's one of the most important events in the history of the universe. In a nil instant, free quarks and gluons were swept up into bound states. The strong force trapped enormous amounts of energy into tiny femtometer-sized volumes. Protons and neutrons crystallized out of the quark-gluon plasma like ice forming from cooling water. This was the moment when the mass of ordinary matter was born, not from the Higgs field, which had already been doing its work giving quarks their small intrinsic masses. The mass was born from the strong force trapping energy into stable configurations. Before the QCD phase transition, the energy was there, but it was spread out, carried by free quarks and gluons in a hot plasma. After the transition, that energy was concentrated, confined, locked away inside protons and neutrons, where it would remain essentially forever. The mass you carry in your body today was created in that moment, 1 microsecond after the beginning of everything. The strong force reached out, grabbed energy from the primordial plasma, and locked it away inside. Protons and neutrons that have persisted for 13.8 billion years. Scientists have actually recreated this primordial quark-gluon plasma in the laboratory, briefly turning back the clock to conditions that haven't existed naturally since the universe was a microsecond old. At the relativistic heavy ion collider at Brookhaven National Laboratory in New York, and at the Large Hadron Collider at CERN in Geneva, physicists have smashed heavy atomic nuclei, typically gold or lead nuclei, together at nearly the speed of light. The collisions are so energetic that for a brief instant, the protons and neutrons in the colliding nuclei dissolve. The quarks and gluons are freed from confinement. A tiny droplet of quark-gluon plasma is created, lasting for only about 10 to the negative 23 seconds, before cooling and reconverting into ordinary particles. These experiments have confirmed our understanding of the QCD phase transition. They've shown that quarks and gluons really do become deconfined at high enough temperatures, and that they recombine into protons and neutrons as the plasma cools. This is experimental confirmation of what happened 1 microsecond after the Big Bang. And here's something remarkable about the protons that formed in that primordial transition. They're still here. Every proton in your body, every proton in the Earth, every proton in every star is either one of those original protons or was assembled from quarks that trace back to that first microsecond. Protons do not appear to decay. They are among the most stable objects in the known universe. The current experimental lower bound on the proton's lifetime, established by the Super Kamiokande detector in Japan, is greater than 10 to the 34th years. That's 10 followed by 34 zeros. To put that in perspective, the universe is only about 1.38 times 10 to the 10th years old. That's about 13.8 billion years. The proton's minimum lifetime is at least a trillion times longer than the current age of the universe. It might be infinite. We don't know for certain whether protons ever decay. Some theoretical models predict they should, with lifetimes around 10 to the 36th years or longer. But no proton decay has ever been observed, despite decades of careful searching by experiments involving thousands of tons of water monitored by thousands of sensitive detectors. If protons are truly stable, if they never decay, then the energy trapped inside them by the strong force is locked away forever. The storms raging inside every proton in your body have been raging since 1 microsecond after the Big Bang, and will continue raging long after the last star burns out, long after the universe has expanded into cold darkness, long after trillions upon trillions of years have passed. The energy inside a proton is among the most permanent things in the cosmos. It was bottled up 13.8 billion years ago, and it shows no sign of ever being released. Let me now try to bring all of this together into a single coherent picture, because I think when you see it all at once, the full scope of what the proton tells us about reality is genuinely breathtaking. You are made of atoms. Your atoms are made of electrons orbiting nuclei. The nuclei are made of protons and neutrons. The protons and neutrons are made of quarks and gluons, bound together by the strong force. The quarks have tiny intrinsic masses given to them by the Higgs field, masses that account for less than 1% of the proton's total mass. The other 99% is energy. The kinetic energy of quarks and gluons moving at or near the speed of light. The energy stored in the gluon field. The energy of virtual particles flashing in and out of existence. All of this energy, through E equals mc squared, manifests as the mass you feel when you pick up a rock or step on a scale. The atoms that make up your body are overwhelmingly empty space. If you could see an atom at the right scale, you'd see a tiny nucleus surrounded by vast emptiness with electrons somewhere at the far edges. The nucleus itself occupies a trillionth of the atom's volume, and that nucleus is made of protons and neutrons that are themselves not solid objects, but contain storms of energy and force. And the quarks inside those storms are point-like particles with almost no intrinsic mass. Layer after layer, as you peel back the structure of matter, what seems solid dissolves into emptiness and energy. There is no solid core at the bottom. There is no fundamental substance. There is only energy, arranged in patterns bound by forces, manifesting as mass. What we call matter is really a pattern of energy held in place by forces. The strong force confines quarks and gluons into protons and neutrons. The electromagnetic force binds electrons to nuclei, creating atoms. The electromagnetic force also binds atoms into molecules. Gravity collects the molecules into planets and stars. At every level, it's forces shaping energy into structure. And at the most fundamental level, inside the proton, the mass itself is energy. This is what the proton tells us about reality. The universe is not made of stuff. It's made of energy and forces. What you experience as solid matter, the feeling of a table under your hand, the weight of your body, the resistance of a wall, all of it emerges from energy interacting with energy through the fundamental forces of nature. The universe is, at its deepest level, a vast interplay of energy and force, arranged into patterns of astonishing complexity, producing stars and planets and oceans, and eventually, on at least one planet, life and consciousness. And this brings us to perhaps the most remarkable thing of all. You are aware of this. You are a collection of roughly 7 billion atoms, each one mostly empty space, each one carrying a nucleus where storms of quarks and gluons have been raging for 13.8 billion years. You are energy, bound energy, ancient energy, energy that was trapped inside protons 1 microsecond after the Big Bang, and has remained trapped ever since, assembled over billions of years into stars that forged heavy elements, scattered by supernova explosions into clouds of gas and dust that collapsed into new stars with rocky planets, on one of which chemistry became biology and biology became consciousness. And now that consciousness, you, is contemplating the very forces and particles that make it possible. Every atom in your body was once inside a star. The carbon in your muscles, the calcium in your bones, the iron in your blood. These elements were forged in the cores of massive stars that lived and died billions of years ago. When those stars exploded as supernovae, they scattered their heavy elements across space. Those elements eventually coalesced into our solar system, into the Earth, into you. And at the heart of every one of those atoms, inside every proton and every neutron, the strong force has been holding its energy in place since 1 microsecond after the beginning. The energy inside your protons is older than the stars that made the atoms. It predates the Earth by billions of years. It predates the Milky Way. It was created in the very first moments of the universe's existence, and it has endured through everything since. The proton is not a simple particle. It is one of the most complex objects in all of physics. A bound state of quarks and gluons whose mass is almost entirely energy rather than substance. It's a storm that never dies, a fire that never goes out, a knot of force and energy tied so tightly that the universe itself may not live long enough to see it come undone. And you are made of trillions upon trillions of these storms. Every cell in your body contains billions of atoms. Every atom carries protons and neutrons at its heart. Every proton and neutron contains this raging tempest of quarks and gluons. Right now, inside you, more energy is bound up in strong force fields than you could possibly imagine. You carry the power of the strongest force in nature within every fiber of your being. You are not solid. You are not still. You are not stuff in the way you've always assumed. You are energy. Ancient energy, born 1 microsecond after the Big Bang, forged in the hearts of dying stars, assembled over billions of years into something that can wonder about its own existence. You are the universe's energy, organized by its forces, given form by its laws, and somehow, against overwhelming odds, aware of itself. The next time someone asks you what you're made of, you can give them the simple answer. Atoms, protons, neutrons, electrons. But you'll know the deeper truth. You're made of energy, almost entirely energy. The energy of the strongest force in nature, trapped inside the smallest structures in existence, holding the universe together one proton at a time. And the equation that makes all of this possible, the one that connects the storm inside a proton to the weight you feel when you step on a scale, the one that connects the fire inside a star to the warmth of sunlight on your face, is still the same 5 symbols that a 26-year-old patent clerk wrote down in 1905. E equals mc squared. It's not just an equation, it's the secret of what you are. Thank you for joining me on this journey tonight. We started with something you could touch, a table, a rock, the solid world around you, and we peeled back layer after layer, going deeper and deeper into the structure of matter until we reached the heart of the proton. And there we found something astonishing. Not a solid core, not an ultimate substance, not the final building block of reality. We found a storm, a contained explosion of quarks and gluons bound by the most powerful force in the universe. A storm whose energy is what gives you your mass, your weight, your physical presence in the world. The proton is not what you were taught. It's not a simple little ball sitting in the nucleus. It's a bound state of extraordinary complexity, held together by a force that defies our everyday intuitions, carrying energy that has persisted since the first microsecond of the universe's existence. And you are made of these. Trillions upon trillions of protons and neutrons, each one a contained tempest of energy and force. You are walking, breathing collections of bound energy. Stardust, yes, but more than that. You are storms, ancient, unimaginably powerful, and still raging. Remember, the next time you feel the weight of something in your hand, the next time you press your palm against a surface and feel it push back, you're not feeling stuff. You're feeling energy. The energy of the strong force, locked inside protons for 13.8 billion years, making the universe solid enough for you to touch. Good night, and may you never look at matter the same way again.